known to various of us, and what I just read here is a correlation-based imaging technique called XC2D, and you're monitoring track work. And I'm not going to say more. I'm looking forward to see what you have to present.
Thank you.
Here's a
Good afternoon. So I'm Patrice Masson with the University of Sherbrooke. I'm here today with the PhD students. So what we'll present here is essentially a new imaging approach, and we start by presenting, in fact, who we are. The University of Sherbrooke is located in Quebec, Canada, not far from Montreal. The GOES was founded in 1984. It's actually the largest Canadian academic research center in the vibration and acoustics. It comprises over 60 people. 6 professors, postdocs, research assistants, and technicians are part of the GOES. The GOES is active in acoustic materials, vibro and aeroacoustics, test and characterization, and SHM in active control. The activities in NDT and SHM started at the GOES in 2001 with 3 professors, research assistants, and graduate students. We have state-of-the-art equipment, including a rapid acquisition system, 3D laser vibrometer, and commercial NDT and SHM system. SHM activities at the GOES include PZT transducers design and configuration, including sparse and compact arrays, advanced signal processing with time and space transforms, guided wave propagation models, including FEM and SEM, experimental characterization of material properties, and damage imaging algorithms for SHM and NDT. In this presentation, we show the application of the excited imaging technique for SHM. The technique is based on the use of a piezoceramic array, where one element of the array is used as the wave generator. The waves propagate into the structure and encounter features in the structure. Afterwards, when a damage appears in the structure, we send again a signal using the emitter, and the waves propagate in the structure and will interact with the defect. The signal is sent back to the receivers and recorded. We then subtract this signal from the baseline that we measured previously. To get the image, we define a grid for the inspection. And for each point on this grid, we calculate a theoretical signal corresponding to a given propagation path. After, we correlate the measured signal for this path to the theoretical signal, and we get the image. We have applied the imaging technique to aerospace. So we have extracted H stabilizer, where we have defined a configuration for the SHM system. So we would use piezoceramic arrays bounded on each bay with minimal footprint. So each bay would be independent from each other. So we have extracted one bay and defined a lap joint structure with a rivet line. We manufactured a riveted lap joint made of aerospace-grade aluminum. On this lap joint, we mounted a compact PZT array of 8 elements. We then cycled this structure using a sinusoidal row. This was done in a test machine, where the goal was to propagate the crack and to monitor it as it propagates. What you see here is the propagation of the crack accelerated 25 times. At regular intervals, the piezoceramic array was used to generate and receive propagated waves in the structure. And we were able to monitor the crack propagation up to complete failure. Here is a typical imaging result obtained with A0 mode after 150,000 cycles. With appropriate signal processing, only the reflection from the crack and from the change of contact force are apparent. We have obtained images as the crack was propagating with the same inspection parameters. As you can see, the spot size increases with the number of cycles. So we can not only localize but also follow and give a severity level associated with correlation. So in summary, we have presented the activities of the SHM team at the GOES at the University of Sherbrooke in PZT transducer design, advanced signal processing, guided wave propagation models, and imaging algorithms. And we have shown the application of the excited imaging algorithm to a real aerospace structure. We would like to thank our supporting organizations. Thank you.